We'll get going. So we are into Thanksgiving week. This is always a weird week for you freshmen. This is always a weird week because you kind of have some classes, but you're already thinking about Thanksgiving, and it's a little wacky. So we're no labs this week because there's no, well, we could have had labs tomorrow, but I know a lot of people are going out of town early, so we're just not going to do it this week. One more lab next week. Okay, the only problem with Thanksgiving week is that you probably have a mounting amount of work to do in all your classes, right? And you just want to go home and eat turkey, right? Instead of doing all that work. So I would urge you to at least spend a couple hours a day like trying to think of this project, the homework 6 project, just because that'll at least keep it in your brain. Okay, Alex, thank you for the reminder. Tonight, instead of lab tonight, if you want to go to a kind of a review session / how to build a hash table session, I'm going to give it. It's going to start at 6:30. I'll be there all the way till 9:30, but it won't last that. I mean, it won't like me talking won't last that long certainly, but I'll stay the whole time, and you can come in and out if you want. Basically, what I'm going to do is hopefully by the end of that, if you want to build a hash table for your project, you will have something that will like pretty much drop into your project by the end of that. Okay, so this is if you are like worried about that. If you're doing a try and whatever, not going to be quite as helpful. But tries, I think you can probably use the previous try stuff a little bit easier if you want to modify that. What else was I going to say on that? I've put up some kind of test results from my own program that I wrote, this song search, and you can look online for that. It's on Piazza. And I'm still trying to figure out exactly how I'm going to grade it, because you can't just do your output is not going to necessarily look exactly like my output, right? Because I said that you don't have to worry about sorting like songs where there's the same number of hits, like 5 is 5, and I don't care which order it comes in. So it'll be a little bit trickier to grade, but I'll try to have a provide thing up by like the end of the week, something like that. Okay, questions on homework 6 at this point? How many people still haven't talked to somebody about their project yet? A couple people? I can stick around for 15 minutes or so after class today if you want, or tonight. Come by the review session after about like 7:30 and I can chat with you as well. Sorry? Oh, it's just going to be 116 in Halligan. Yeah, whatever the lab is there. And we shouldn't have any problems because technically our lab should be there and it's not happening, so we should be able to be in it. Okay. All right, anything else? Okay. So I did want to spend a little bit more time talking about the project itself. In particular, I wanted to talk about how to sort using a vector if you want to use the built-in sort function. I'm allowing you to use that if you want. However, I also did some tests this weekend, and we'll get into it in a second about what the best way to sort like that list of 10 songs is, and it might not be this way, but I'll show it to you anyway. Then we're going to go back and talk about skip lists. One of you will get one of these fancy coins. I have a penny, or a nickel, or a dime, or a quarter. It's your choice, whichever coin you want. One of you will get that, but you will have to pay a price for it. In that you'll have to help me out with the what we're going to do, but it's not hard. Okay, and you'll get a whole like coin out of it. So that's what's that? Well, yeah, it is a fifth of your laundry. There you go. Well, unless you pick the penny. So anyway, so then we'll go into this other kind of data structure called a Bloom filter, which I think is also a very unique data structure. Another one that if you get to an interview and somebody says, how are you going to do this? And you say, I think I'd use a Bloom filter, they'd perk their ears up and go, oh, this person knows something. So we'll do that. And then we'll start talking about these things called ropes, just a real brief intro to that, and then we'll do more of that next week. Just to finish out the semester, by the way, let's see, after today, there's 3 more lectures, next Monday, next Wednesday, and the following Monday. The last one will be a review, kind of like we did a mid-year review before. Next week, probably Monday we'll continue with like ropes and some other data structures, and then Wednesday will be a Comp 40 preview. So if you happen to be taking Comp 40, you can come to that lecture and I'll go through kind of the things that I think you should do to prepare yourself for Comp 40. And it doesn't mean you don't, like, it doesn't mean that if you're here and you're not taking Comp 40, you're not going to learn anything. I mean, we do talk about a couple interesting like comments, but it's not like it's going to be mandatory. Not that any of it's mandatory, but it's not going to be like, I really like you have to be here. I mean, if after the beginning of class you want to get up and leave, I'm not going to worry too much about it. But if you're taking Comp 40, I would urge you to stick around for that lecture. Okay, so you had a comment?
Yeah, so you said next Monday, next Wednesday, and the following Monday?
Next Monday, next Wednesday, and following Monday. I think that's it, right?
So there's no
That's it.
class Wednesday?
This Wednesday is right, we're already on holiday break Wednesday.
All right.
Yeah, this Wednesday.
Which my
This Wednesday, right? No classes this Wednesday, yeah. Okay. Yeah, there's only 2 days of classes this week. Today, tomorrow.
wish my company followed the same schedule.
Well, there you go. You should work for a university. Okay, all right. So, question for you. All right, what's the best way to sort your top 10 songs? Okay. First of all, I don't know how you're going to store your top 10 songs. That's completely up to you. But what's one way that I might have suggested that I did suggest on how to sort your how to keep your top 10 songs? What is it? Well, what about the actual storage of it? An array, right? So yeah, so I'm going to write it like this, even though it doesn't really matter. But here's your array, and we said that it's going to have at least 10. What was my suggestion was to put 11 in here, right? Because, right, this is going to be 10, 0, 1, 2, ... to index 10, which is the 11th song. What was the reason for that 11th one?
Have a working one.
Go ahead, Vinal. Well, not necessarily so you can use insertion sort, although we can, but
So you can leave it, and so when you're working on a song, you can leave it there and come back to it later.
yeah.
Insert it when you're ready.
Let me do this. Let me break this each little bin here is going to have a couple pieces of information in it. And you guys have already you might have already come up with a separate way of doing this. But let's say that part of the information is like an index for the song. So song 1, some index, song 22, song 43, song 89. Actually, it doesn't need to be in any order. That could be song 8. Right? Song 22, 8, whatever. And then a frequency of how many times that word occurs. So this is like the bucket, either a hash table or your trie or whatever other structure you're using. This is the bucket for some word like hello. Right? So hello, this is the hello bucket. Song 1 might have, 14 instances of hello. Song 22 might have 11. Song 8 might have 7. Song 89 might also have 7. And then this 10th, and then down all the way to 10. And then the 11th one, we don't know how many it's going to eventually have until we're done reading in the whole song. Right? So that's why Aaron says, oh, it's going to be like a working copy. Right? So this might be the song we're working on. Song 100 is what we're working on. Right? And song 100, it starts out at 1, and then we find another hello, and then we increment it to 2, et cetera, right? Okay, question.
Keep going, because I'll ask at the end.
Okay, so now this is kind of what you might have as a setup. Now you might not keep this sorted as you go. I did some tests this weekend, and I thought about this, and so Senna, what were you saying a good way to sort this would be? Why insertion sort?
Because then like almost sorted every time.
If you keep it sorted every time, it'll be almost sorted every time. That's the first thing. The second thing is how many, like every time I get a new word that fits in this bucket, how much am I going to increment this by? Just 1, right? So the next time I get it, it's going to be 3, then it's going to be 4, then it's going to be 5, then it's going to be 6. At what point, given this current table, am I going to have to move it out of this 11th bucket? When it makes it to 8, right? Now, when it makes it to 8, I could have to move it all the way to the top, right? What's the only case that would happen?
15.
If every single one was 7, or in this case, if it was 15, I would have to move, but it would never get to 15 before it would get to 8, all right? Because they were counting up, right? So in this case, unless every other one is 1 less than what this just got to, it will only have to move up a proportion of that, not all of them, right? So in other words, insertion sort's a pretty good sort in this case because you're just going to go and you're going to say, where does it need to go? Swap, 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 swap until it goes there. So song 100 in this case, you'll check it against 89, right? 89 will go here with 7. And then 100 will be here, and it's going to be 8. And then you'll check it against this one, right? And then you'll swap it. Song 8 and 7, 7 frequency, and then you'll have song 100 and then 8. And then now you check it with this one and you're done. And you see how we only had to move it up a few. We did not have to move it up the whole way. So that's actually a pretty good way to sort this because it's going to be quick. What's in particular, which way did I sort this, by the way? Did I sort it from here down? No, I sorted it backwards because you're going to have a small one that you're trying to insert and it's got to go all the way up. It might, like remember, it's probably only going to go 1, maybe 2, maybe 3 in some weird cases, but it's not going to go all the way to the top. So sorting it backwards actually helps out in time-wise. One sec, yeah.
I mean, it's not going to save too much time because they're small areas, but couldn't you also just not swap it as you go, just keep checking?
Yeah, sure. You could keep checking. Yep. But then you'd still have to swap these ones, right? I mean, you'd have to move them. You'd have to move the rest of them.
Wouldn't you not have to because eventually?
Depends. Do you want the whole thing to be sorted first?
Well, I mean, I'm thinking if they're all, like, say they were all 7s, and you
Yeah.
just swap it out, why do you care which 7 you're not showing?
No, that's true. But then you've got more logic involved too. But either way, let's say it had to go all the way up here. These ones all have to shift down, and swapping is a pretty efficient way to do it. Not the most, but a fairly efficient way of doing it. Yeah. Okay. Somebody else had a comment. Yes, and then Jen. Yeah.
So if you're just swapping, isn't that just like the bubble sort?
It is not just the bubble sort. It's actually it's bubble sort is bubble sort is like slightly different. I don't even remember the bubble sort in that case. But yeah, I mean you're kind of doing that. But bubble sort is where you're going for all of them, sort, swap, 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 then swap, swap, swap. So it's not quite. Not quite. Yeah. But this is I mean one of the ways of doing a relatively in place, like an efficient in place one is to just swap them. But you're absolutely right. You could keep this one out and then move, and then just plug that one in there. And that's really the same idea. Yeah. Jen.
I have a question with counting the frequency of the word.
Counting the frequency of the word, yeah?
If we do it this way, that means we'll have to go through the song, like the number of times we have distinct words, right?
No, you do this as you go along. Okay? So if I have a song, and I think the song I used before was Mary Had a Little Lamb. Mary had a little lamb, blah, 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 lamb, blah, blah, lamb. Right? Let's say there's lots of other words in there. Okay, as you're going through, you're going to get to this word, you're going to put it in the hash table. You're going to update the frequencies. You're going to get to this word, you're going to update the frequencies. You're going to get this word, update the frequencies. Get to this word, update the frequencies. Get to lamb, update the frequencies. The next time you get to lamb, it's going to be the same thing. You're going to go back to the same place in the table, update the frequency. But you only have to go through this once.
So which means you still need to go through your hash table to like.
You have to go, for every word here, you have to go to your hash table once. Yeah.
But
You have to search it once. Yeah.
when you search it once, okay.
And then insert it once. But remember, hash tables are fast. Order 1.
Yeah, but at the end you will need to keep the song you're working on at the 11th.
Yes, you have to keep it
until you're done, right?
until you're done with the song. But at that point, it should either have moved up or it's still at the 11th and then it's not in the top 10, so who cares?
So
Right.
as you keep going, you keep sorting.
Yeah, you keep sorting it each time. That was what we decided. Now, either you keep sorting it each time or you keep which one the minimum one is and then sort at the end. That doesn't matter either. Either way, it's just about as efficient. Jean-Marie?
I'm wondering how, if you're sorting while you're going, how you know where your song is, like at which end.
You have to search one each time.
Okay.
But search from the back, search from the reverse, because it's probably going to be near the bottom. Not always, but probably.
So why is it better to sort as you're going if you're going to have to research it?
Well, you've got to, so you're saying keep a pointer to the minimum one? That,
Just keep it at 11
And then when you're done with the song,
I know. How do you know when you're done with the song? You're on to the next song. I'm just saying that's more logic. You can do that. I'm just saying, no, hold on. No, then you have to go through the lyrics again. So you're wrong in that. You got to go through the lyrics again. Yes, you do. You have to go, hold on. You can leave it at the 11th.
the words that there are, yeah.
Hold on. You have to leave it if you leave it at the 11th, that's fine. But when you get to the end of the song, you have to go back through your entire lyrics to go update them all again. That's fine, but you have to do that, right? So it just would mean you have to go through the lyrics twice, which is fine. I mean, and you can check the doing it. The way I did it yesterday when I did this, I got it working with the sorting each time, and I thought it would be way slower. It's still 2 minutes flat to do the whole database. So I got it down to 2 minutes, which is pretty good, all things considered. Okay? Yes, and then back there, yeah.
Is it necessarily faster to be just storing 10 than to store everything and then go through and sort after?
So, well, okay, so you're saying just keep doing it. Now, you're going to run into issues with, like, that would take a huge amount of space, right? Because you're going to now have, the is 170,000 songs worth of thes, right? You can what? You could use a better sort in the end. You could well, the best sort in that place, believe it or not, would probably be a selection sort. Because in that case, you just want the top 10, so you stop after 10 and you're done. You don't sort anymore. But so you can do that, but you're going to run into huge memory issues there. That's the only difference there. Okay? Yes. Yeah.
So,
Jake.
are you like doing this array top 10 sorting thing? Is this like as you search for one word specifically, or are you doing this as you read in the songs for the first time?
Read in the songs for the first time. Well, depends. You can do it either way you want. You can either, you need to kind of keep the top 10 in some form that you know. Now, it could be 11 or whatever, but you're going to have 10 or 11 songs that you're going to need to eventually sort. Doesn't matter to me. I just think that it's not so bad to keep it sorted, and if it's already sorted, as Susanna said, it's going to be relatively quick to keep sorting because you're only going to move 1 or 2.
Right. So you get to pick whether or not you want to take more time in terms of like loading the database versus searching?
Yep, you can pick whichever you want.
Okay.
Yep, you can pick whichever you want. Yep.
Would this be better than using a heap?
Would this be better than using a heap? I think it's probably about the same as using a heap. I mean, the only problem with a heap is as you remove things from the heap, you got to store them somewhere and then stick them back in the heap later. But that's easy if you do.
What do you mean?
For a heap, you only know where the top song is,
Yeah.
right? You don't know any of the other ones. They're all out of order, right? So, but then when you're ordering them, you remove, bubble up, remove, bubble up, remove, bubble up until you've got a sorted list. But then you're not in the heap anymore. So you have to go back and put them back in the heap after you get done sorting them.
So you only take them off when you want to search.
Yes. You only take them off when you want to search. So you're right. It's quick to do that. So that's fine. But you just have to keep in mind that is what, because if I search for hello twice in a row, the second time you'd go, nope, no songs have hello, all right? If you didn't put them back in. Yeah, that's the issue there. Okay, somebody else had a question over. Okay, no?
Can I ask a question about
Oh, yeah, you.
vectors?
Yeah, you can ask a question about vectors.
Do you have to destroy it at the end? Like how do you?
It depends how you create it. If you say vector string lyrics, right? Under the covers, the compiler is calling new and delete on this. So you do not have to do it. You only have to call delete if you actually use the new command.
Okay, so like if I make a bunch of vectors, then I don't have to.
Don't have to delete them.
in the destructor with those.
Nope, you do not. If you do them this way. Now,
Yeah.
you might do something like new vector blah, blah, blah. You could do that. But you probably won't need to.
Okay.
I may have in one case in my program, but that's it. Yeah, Charles?
So one thing I'm kind of confused about is that the assignment is kind of two portions. There's building the database and there's searching it.
Yeah.
What I don't understand is since we've been given, there's a bound on how much memory we can use.
More or less. You can use, up to 10 gigabytes or something crazy like that, but yeah.
But I don't see what's stopping us from just pre-searching everything and storing that. And then
You would run out of memory if you tried to do that, if you tried to pre-search everything. You kind of are doing that here. You're really doing that in some sense, right? The hash table is going to keep the songs where the lyrics happen. So you are kind of doing a pre-search of everything in some sense, yeah. Yeah.
Two related questions.
Yeah.
When you have vectors, can you set two vectors equal to each other, and does it know how to do
Yeah,
that?
you can. Vectors are good about copying. Now, it depends what's in here. If it's a string, yep, you're fine. If it's your own, like if it's a song with frequency or something like that, and this is a pointer, that's probably all right if you don't care that the pointer gets moved somewhere, but it does not do a deep copy. It will copy whatever this is according to whatever this is able to be copied. So normally, yes, you can set two vectors to each other. You probably don't want to do that too often because it does have to copy everything from one to the other, and that's slow.
Now, what about when we, so your vector here, or your dynamic array here, or
Yeah,
regular array,
vector, yeah.
whatever it is, you have said it's a bunch of structs of the name and then the frequency?
I wouldn't call it the name. I'd say it's the index into the song. Although you could also keep a name if you want to make it a little quicker, but yeah.
Okay, so whatever it is, it's like it's a struct, it's not one thing.
Yeah, it's a struct.
So when you're doing your search and you're moving them,
Mhm.
where do you write your copy constructor for each struct?
Yeah, you don't actually, well, it depends how you do it. Where would you would write that in the class of this, in the,
It's a class, not a
well, actually structs can have copy constructors as well.
Where do you put them?
Inside the struct. Well, I mean, you have a struct, you can have a header file, and then you can also have a, header file for a struct if you want to. And then you have the actual struct itself, and they're really identical to classes.
Structs can have functions.
Structs can have functions, yeah.
So if you
Not in C, but in C++ they can. Yeah.
If you have a header file for a class, and in that header file it defines a struct,
Yeah.
do you define the copy constructor for that struct in the implementation file for the class?
Sure, you can do that.
And do you
Yep.
just write it the same as
Yeah, you'd write if it's struct, right? X, you would do X : and then the function name for the right. It'd be X and then the const left-hand side business, same as before. Yeah. Aaron and then. Yeah.
So, is it dangerous to pass vectors to functions?
That's a good question. Is it dangerous to pass vectors to functions? It's dangerous in that it takes time. So you don't want to do that if you can.
Does it copy everything? Does it
Copies
pass
everything.
by value?
Yes, it copies everything out of the vector. Yeah, so you would want, you can,
And then you can modify the original.
and it doesn't modify the original. You can pass by reference, which would work fine. You can pass by reference, which would work fine. You can pass by pointer. In the one I did, I passed by pointer, and the syntax is just hairy. That's all. Syntax gets a little crazy, but you can do it. Yeah.
Do you need to create a unique constructor for a struct, or can you just be like new X?
No, generally you could do new X thing, yeah. But if you're doing a copy, you wanted to copy the struct and it needed to be a deep copy, you'd have to write a copy constructor, et cetera. Or actually more of an assignment overload, probably.
And when we're making a new struct, is it struct dot attribute equals, or do we use the pointer arrow?
It depends. If it's a pointer to a struct, you use the arrow. If it's not a pointer to a struct, you just use the dot. Okay, so let me move on here with what to do if you do want to use the vector sort. Okay, because some people might want to use the vector sort for this, right? You can do that, but you have to set it up. Now I'm just going to briefly go over this. Online I put the full example of this, but I want to show you what you can do. It's actually pretty neat. If you have lots of stuff to sort, you can do this really neat. Here's what we have here, okay? So this is from, it might be the way you decide to write your thing. Here's your struct. It's got a song pointer, and it's got a frequency, right? And then I create a vector, which I call songs with freaks, which is just a bunch of song with freak things, right? Okay? And we've created that. And then what happens is you just call sort on the beginning of the list, or the vector, and then the end of the vector, and it sorts it. But can you tell me what I have to explain about this if you're trying to sort song with freaks? What's it sorting by, right? Is it sorting by the song pointer somehow, or is it sorting by the frequency? What do you probably want it to sort by? You want it to sort by the frequency, right? So we have to tell sort, hey, sort it by frequency. Well, it turns out, if you're sorting things, let's just pretend how you're sorting things. If you're doing an insertion sort, what do you decide? If you want to move this to here, what do you have to do? What do you have to make a choice between? What do you have to compare? You have to compare the frequencies. How do you compare two things? If thing 1 and thing 2 do something, right? What's right there? A less than or an equal than or a less than or equal to or whatever, right? That less than is what we're going to overload to tell our sort to sort by the frequency. So we have to overload less than. It's just like overloading equals, right? And here's how it works. Okay, you ready? It's going to return a Boolean because you want to know if one thing is less than another. It's true or false, right? This is the operator which tells you we're overloading less than. You pass in two things that you're overloading, like song with freak 1 and song with freak 2. right? We call that the left-hand side, LHS, and the right-hand side, RHS. So far, so good? And then it's a pretty simple function. If the left-hand side frequency is less than the right-hand side frequency, return true. If it's not true, return false. We've just overloaded the less than sign and said that's what less than means. So when we go back here and it sorts it, it says, oh, I'm going to use less than. It says, is there a less than for songs with freak? Yep, we created one. Ta-da! It sorts it. Yeah?
When we use the overloading operator in this case, does that mean that every single time that the compiler sees the less than sign, maybe in some different context, it's going to have to check to make sure that the two things it's comparing aren't those? Is it checking like the clause of what it's?
Yeah, good question. When you're overloading this operator less than, it looks for two parameters, this one and this one. And if they're not song with frequencies, it uses whatever else it is. So basically, the compiler says, when you call that sort function, it assumes you're calling less than with these two things, and it'll complain if it doesn't have one of these. And that's how it knows that it's the right one. Yeah?
So it'll only overload the less than sign when you're calling the sort function?
Yes, it'll only overload less than when you call the sort for songs with freaks. It's just like when we did operator equals overload. We didn't overload equal for every equals, only for the ones that we wanted for that class. Yeah?
Is there a way, so I'm assuming sort's going to start at position 0 and work its way to the highest position?
Sort's going to start from the one that you start it with, in this case begin, which is the first one.
Go from end to begin?
Ah, you can go from end to begin. There's different ways of doing it, but if we want to sort from high to low, you can't actually go in this direction. Like it's generally a quick sort is what it is under the covers. But you can't go from, you can basically say go from here to here. But what it's going to do is if we wanted to sort like this one, if song 1 is less than song 2, would always sort it in the same order you did for your homework assignment. The least one on the top. Least, all the way down to the greatest. We actually might want it in the reverse. You could do it in that way. But if we want it in the reverse, guess what we can do? We can actually overload the greater than operator. But, right, we overload the greater than operator. It's exactly the same, right? But we now have to call it and say, hey, we're going to use this thing called greater than to compare it. Okay, and it will do it this way. It's not going to, if we don't have this parameter, it calls the less than. If you want to use this one, it calls the greater than. Yeah?
Can you like trick it by saying the operator less?
You totally could trick it. Yeah, you totally could trick it by changing your function here. You could make this just always return true. Or you could say, if flip a coin, it becomes false. Right? It just doesn't even, I mean, it's completely up to you what you write there. So you totally could trick it. But you probably don't want to do that to the people who use your class later. Right? That's mean.
It's like those people who put like define true false.
Right. You don't want to trick people like that unless you're writing the obfuscated C or something. Okay? All right. So this is how you do this. Now, again, the full example is online. If you want to go look at it, you can run it. You can see what happens. It actually runs and sorts a bunch of these things by ascending, then descending, and all that. And it's kind of nice. Okay? Question?
So for this one, you said insertion sort was probably the best way to go.
Yeah, insertion sort this is probably not the best way to go for 10 songs. Although this may be using insertion sort under the covers. I don't know because of the shortness of the array.
So would we lose a lot of time if we just implemented it that way versus?
No, you won't lose a lot of time. I'm saying you can do it either way you want. I just wanted to show you this in case you ever wanted to use it. And you might want to use it. I mean, if you are keeping a list of all the songs, you might want to sort them.
Because then that way we wouldn't have to worry about all the corner cases of like they're all 7s versus, and then you have to.
Right, you wouldn't have to worry about the corner cases, yeah. Although you shouldn't anyway. You've got to be careful. You shouldn't necessarily have to worry about those. Yeah.
How do you know that it's less than?
By definition, it uses it when you don't put, where did it go here? When you don't put a third parameter, it uses the less than.
Yeah, so we would just go look it up in the library.
Yeah, you would look it up in the library. But if you want to use some other function, you can use any function. This one happens to say, use the overloaded greater than sign. You could also make this any function. As long as it returns a Boolean value, you can use it. Yeah, and as long as it takes a song with freak on one side and a song with freak on the other. So it's got to do that. Okay? All right. Okay, so that's how you use vectors to sort. Kind of an advanced like C++ topic, but it's kind of neat if you want to use it. Okay? Other questions on that? Okay, let's get back into our fun skip lists. Okay? Remember last time we said, hey, skip lists are pretty neat. We derived a whole bunch of different ways, or we derived the best skip list ordering, or how many lists, I'll show you the actual list in a second, we determined that if we have log n lists, right? List 1, list 2, list 3, log n. If we had log n lists and they were separated by the next one up had half, 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 we got a beautiful logarithmic behavior for searching a skip list. Okay, if it's taking a second to come back to you, that's okay. But remember, I'll just draw a quick one here, right? We had a skip list here where and remember, this was like the New York City subway, right? You have all these different nodes here, right? And this could be 6, 18, they have to be sorted, 23, and 45, right? And then if you have half in the next list, right, 6, and then I guess it would just be, I guess we'd be done at that point, wouldn't we? Oh no, yeah, we'd have 2. We'd have this and this, right? So I guess this is not the best example in the world, but 45, right? And like this. And if we had 8, right? If we had more like 6, and then, whoops, bad choice of where to start. Hold on. We start it like this: 6, and then 9, and then 18, and then 19, and then 23, and then 30, and then 45, right? Like that, like that, like that, like that. Notice this is looking a lot like a binary tree in the sense that it goes half, 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 like double, 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 right? Which is a binary tree which it acts a lot like that. Believe it or not, this is actually slightly easier to create than a lot of binary trees, especially for some of the ways you can actually, like it's easy to create linked lists, right? Even though I keep saying linked lists are slow, when you use them in this form, they're pretty fast. Take up a little more space, but they're fast. Okay? All right. So we've got the linked list. Actually, do I have it? Yeah, of course I do. Got it right here. Okay. So that's how it looks, and this is how you search, right? Forgot this one. Right? You search it by saying, okay, I want to find, let's say I want to find 19. Well, I start at 6, and I check the next, and that's too big. So then I go down, and I check the next one, and that's not big enough, so I go down, right? And then I go over. Actually, I would check this one too big. Go back, check, go down, and then check right here, and that's it. So it's a nice like logarithmic path you take. Okay? This is optimal. The question is, how do you actually build this in real time? If we knew all the things, like if we were in New York City and we knew all the stops ahead of time, right? We could build this using perfect math, right? You could build it so that you have all the stops and then you have the half, 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 half. You could do that. But if you have no idea how many stops you're going to have or how many nodes you're going to have, how do we build this efficiently? Any ideas? Ben?
I'm thinking you could just do it. I'm thinking you could just place the upper nodes after it's finished.
I tell you what, take a couple minutes and think about this. Think about different ways of creating from scratch. So here's what I'm going to do. In a few minutes, I'm going to say, give me a node, and you're going to say 17, and I'm going to write it down, and then I'm going to say, let's create a skip list from this, right? And then I'm going to say, give me another one, and you're going to say 25, right? I'm going to do 25, and then at some point I want to create a skip list, meaning I'm going to have more levels. But I want you to tell me whether, like, when I need to, like, add or take away various parts. So think about that for a minute. Talk to your neighbor. Just say, look, how might we build this thing efficiently? Go ahead, talk for a minute or a few minutes.
Then we can just do that the answer.
Okay, who thinks they have a good idea? I know I heard Jordan with a relatively good idea. Who else thinks they have a good idea? Somebody hasn't spoken in a little while. Somebody in like the back center there. You guys are smart. Grant, what did you guys think? Oh, very confused. Okay, so let me start you off. Let me just start you off, and you can tell me maybe what you're thinking. 25. Okay, no other links. Do we need to do anything else there? Probably not. Okay, so what's next? Let's say 30. I put 30 in, and by the way, the bottom list is going to have every element. That's the definition of a skip list, right? That's our invariant. The bottom has every element. Okay, 33, and then what? Do we do anything yet? Okay, don't do anything? Okay. What's then 48? Okay, what do you want to do? So you're going to create two new levels, like two things up here, 25 and 48, and like that, and then like that. Okay, you're starting to take a little too much time. I'm sorry, Grant, you don't have enough time to do that. Good idea. Good idea. And what you're probably doing, and I heard some people say, I think Jordan, overheard you say, what you're going to do is like every fourth one, like every power of 2, you add another level or whatever, right? That's fine. That is a way to do it. It's just going to take too much time, right? Because once you get to, once you get to like a ton of these elements, you're going to have lots and lots of like all of a sudden copying to do, and it's going to take too much time, and that like ends up going down into linear behavior, which is not really what you want. Yeah.
What if we use recursion to do this? So like passing in the amount of nodes you have, but also like the range.
Yeah, you can totally use recursion to do this. It's just going to take time, right? Because you still have to copy all these things, right? So that's kind of the issue, right? Is the kind of the issue. Yeah, go ahead, Rebecca.
Maybe make like a new pointer in the node that points from 25 to 48 and call that like have a new level of pointer.
Oh, you mean inside here? You could do it that way. It makes it a little trickier because then you don't know how many pointers you're going to have in here, and then you might need a linked list of pointers in here, and you're basically doing the same thing, just not as like defined space-wise. So you could do that, but really you haven't changed the problem at all. You're doing the same thing, but good idea. Yeah, good idea. Anybody else have another idea? Yeah, Charlie?
Would it make sense to write it out as a binary search tree and just add the nodes?
Would it make sense to do as a binary search tree and add the nodes? Probably not. Again, you're probably either going to take too much time or you're going to have too much overhead doing all that. Yeah?
Is there a reason that we can't just get the entire list first and then build the
Yeah, I mean, because I'm going to only feed it to you at one at a time, right? I mean, if you did have the entire list at first, fine. Go ahead, take the time to build it the proper way, and then it's going to be perfect, right? But we end up wanting to estimate the perfect nature of this, right? We want to end up estimating the perfect nature of this, right? So what we're going to do, right? We're going to do something a little bit different. This is going to be the first data structure. The first data structure we do something completely wacky on, right? Anybody have any ideas? What wackiness we might end up like laying into this data structure with?
Guess how many there are.
You could guess how many there are, but we're not going to know. I mean, I could give you 5, and then I want this to perform well for 5 and for 5 million and for 10 million, right? Yeah, Jordan?
You flip a coin and decide if you want to make one instead of level up.
We flip a coin. Oh no, that was the quarter, wasn't it? Is it gone?
No, we got it.
Okay. Do you agree that for payment of that quarter you will do a job for me?
Yeah, sure.
Okay. Here's what we're going to do. Okay. We're going to have this has gone into the realm of what we call a probabilistic data structure. Okay. Literally, we are going to use probability to build our skip list. Okay. It's actually kind of neat. All right. Jordan, are you able to flip a coin?
Yes.
Okay. So here's what I want to do. Jordan is going to be our designated coin flipper. Okay, he has been paid a tidy sum of 1/4 to do that. Okay, and he's going to actually use his cold hard cash to do that flipping. Well, unless you want to use whatever, but you do that. Here's the idea. Somebody's going to give me a number that I'm going to put into a skip list. Okay, and there's one other thing we're going to do. All skip lists, all lists have to begin with not -8. That would be weird. No, negative infinity, basically to say that we're always going to have a position to start at, okay? Because you want to start from the top left, and every list has to have one that's always going to be the least amount, just for what it's worth. Okay, somebody's going to give me a number, and I'm going to add it to this skip list. And then Jordan is going to flip the coin, okay? If the coin comes up heads, I add another level with that exact node, okay? And then if it came up heads, he's going to flip it again. And if it comes up heads again, I'm going to add another level. And if it comes up heads again, I'm going to keep adding levels until it doesn't come up heads anymore. Because when it comes up tails, I am done with that node. Okay? Let's see if we can build this. In fact, I'm going to start it a little lower here, just so we can get this as high as we need to. Negative infinity. OK. Somebody give me a number. 17. OK. I didn't tell you to. You're already doing your job wrong. I didn't tell you to flip yet. What did you flip? It was heads? OK. So what do we do on heads? We create another one, right? So actually, I guess it's this way. Create another one. So we still have a negative infinity. And then we go over here, and we create a 17 here, and it points down to there. OK, check. Somebody give me another number. Oh, no. Flip again. Yeah. Although, not really, because you're never going to go. Oh, yeah, it could. Yeah, you're right. If this was, yeah, sure. It would in this case. Heads again. Got to create another one, right? Oops, I did it again the wrong way. 17, negative infinity, and there. OK, flip it again. You keeping him honest. OK. This way, 17, and negative infinity. OK, go ahead. No, are you kidding? Is he really true? Are you really flipping it? All right. That's all right. No, that's all right. It's all probabilistic, which is fine. OK. Go ahead. Flip again. You don't. This is a terrible random number generator. You're doing it the same way, right? You're not like flipping it, and then if it comes up heads, and if it tails, you go the heads. No. OK. All right. 17. OK. Negative infinity. Now remember, this is going to be for billions or millions of nodes, so this is actually OK right now.
Heads.
I'm running out of board space, so 17 and then negative infinity. All right, I did the wrong way. OK, these could be doubly linked lists too. No, you keep forgetting to flip it.
Tails.
OK. All right, give me another number. 42. OK, so 42 goes down here, right? OK, all right, Jordan. Keep him honest, Yenny.
Tails.
OK, tails. All right, give me another number. 5. OK, so 5 has to go down here somewhere, right? I'm going to do it right here. 5. OK, flip the coin. Tail. OK, give me another number. 19. 19 goes out here somewhere. OK, go ahead. This doesn't get interesting for a few more things here. Tails. OK. So, OK, keep going. Another number? 18. Oh, that's kind of mean to me. OK. 18. OK. Flip it. Heads. OK, so 18 gets bumped up to here. Right? 18 gets bumped up to there, and we are good to go. 45. OK, we'll pick another number. 45. What's that? Nathan? Somebody have a comment?
Oh, the arrow.
Oh, no, oh, the arrow down? Oh, the arrow. It doesn't really matter. Yep. 47. Oh, we did have to flip it again. You're right. Flip it again for that one. Head. OK. 18. OK, yeah. OK, tails. So that's it. OK, now we're on a 40. Let's see, 47. I think somebody said OK. 47. OK, go ahead and flip it. Head. OK. So we get 47. And then there. And OK, head. What is it? Tails again. OK, one more maybe? Anything bigger than 47? 60. OK. So 60. Go ahead, Jordan. Heads. OK, so 60 goes up this way. 60. And then there, OK? Tails again, OK. So you see, though, that we're building this, although it's a little wacky here because we got lots of heads in a row. It will model building a skip list. And what we want, remember, is half to go this way to the next level up. And if we're flipping a coin, on average, how many will go up? Half. right? So at each level, you'll get half of those ones on average will go to the next level, next level, next level. This one was weird, but it would do that. Yeah?
How is this any faster than Power V2? Like,
How is it any faster than Power Z? Because first of all, half the time for any particular level, you're not going to go up at all. So that's done. You're done, right? And then for all the other ones, it's
that's true anyway.
no, it's not true anyway. I wouldn't say it's true anyways. No. I mean, you're going to have to, because again, like let's say we added one right now and we did it your way. Okay, we add one. We have to calculate whether or not it's another power of 2, and then we have to add more. We have to add more. Yeah, we don't know them in order either. Yeah, we don't know them in order. We also don't know how many total there are. So there's lots of issues with that, okay? But this is, like I said, this is the first probabilistic data structure. And you can go look up the math if you want. I don't want to go into it right now. But it is probabilistically sound that building it this way will create a skip list that on average, in fact, what we call with high probability, you math people might know about that, probability, there we go, which we normally just abbreviate WHP, right? With high probability, this will be logarithmic search based on building the data structure like this, which means that, and in this case it's not because we haven't gone far enough to average all these guys out, right? But eventually it will look much more like this list, eventually, if you give it enough time, right? And with high probability, it's going to be a search of a logarithmic search, which is kind of what we were looking for. Okay, pretty neat altogether. Yeah.
What's the probability of getting 6 heads in a row?
Not so bad. Probably, well, what is that? 2 to the, yeah, it's 1 to the 32, right? So if we had 32 other classes, yeah, 1 divided by 32, right? 1 out of 32, yeah. Yeah.
So is this called the probabilistic skip list?
It's called, yeah. This is the way we build this skip list is a probabilistic way. I mean, you could call this a probabilistic skip list, sure. Yeah. Okay. So that's kind of neat. You can build this. Question: how do we delete from a skip list like this? What if I want to delete 17? Just delete all the 17s, and you just change the pointers, right? You what? You would have to change all the pointers, yeah. I mean, for each list, you have to delete all of the value that it happens to be in, and that won't be that difficult because on average, there's going to be like this one will have a 17, half the time this one will have a 17, half the time this one will have a 17, et cetera, and you get into good returns pretty quickly in that sense. Jacob, and then. You could have a next and an up. Yeah, I mean, you're going to go, but you want to go from top. You want to start here always. You always start in the bottom, the top, right? Top left. Yeah. Okay. Good. Question, Brad? Okay. Yeah. So anyway, so that's skip lists. Not bad. Interesting strategy here. Here's the strategy in detail. And by the way, I think this is a relatively easy one to remember. Like we've gone through a whole bunch of stuff, but honestly, if I called you up 2 years from now and went, hey, do you remember anything from data structures, and you haven't been practicing a lot of it lately, you'd probably have to scratch your head. You'd be like, oh my gosh, AVL trees, holy smokes, I don't remember what those are. Like I don't remember how to do that, right? All this rotating in business, right? But I bet given a coin, if I gave you a coin, you could probably create a skip list pretty easily, right? Because you'd be like, oh yeah, I remember this. You just create the list and then you flip a coin, and then it's not hard to remember, all things considered. And it's also not that hard to build. So if you want a fairly good data structure, it's not hard to build, skip lists are not a bad way to go. Pretty quick, all things considered. Okay. All right, questions on that? Yeah, one sec.
How do you flip a coin?
Good question. How do you flip a coin? You can do a pseudo random number generator, which is very quick. It's just basically a mathematical function that on average has like either comes up true or false. That's really it. It's you can also do it using real random numbers, but that's not really the best idea because it takes longer to do. But you. A what? Well, I don't know what that is. Oh yeah, you can take two big things, mod them together, come up with another prime, mod another prime, and yeah, there's various fast ways of doing random numbers. that don't need to be perfect, because we don't care if it's perfect for this. We just care that it's good enough. Right? We're not talking about cryptography here. We're talking about getting a list that makes sense. Right? So yeah, that's how we do that. OK, other questions? Yeah. What do you do with the infinity? This is just where you start, right? So if you always start at this top corner, and in fact, you don't even need to, if you're looking at some number, it's always going to be less than that number, so you don't even need to, it's just like a placeholder to basically start where it is. Yeah. Yeah?
If the 18 were to go higher, you would just put the infinity up in 28.
You'd have another infinity up higher, yeah. Oh, yeah, yeah. If the 18 was, yeah, well, sorry, if the, which one? This one?
Any of them that are shorter. Yeah, the 18 went up past the 17.
Oh, past 17, you'd have the infinity going all the way to negative infinity going all the way to 18. Yeah, yeah, exactly. OK. All right. Yeah.
If you were to code that, what would the negative infinity
Would that be null?
Negative infinity would not be null. It would be what? We've used it in a different assignment for the int min or whatever, or float min, or whatever you're using as your structure. Just whatever you define it as being the minimum of that class. Yeah.
Oh wait, so you have to create min yourself? Or define min yourself?
It's probably defined for you. But yeah, you would define it as the minimum. And that's easy. It just means that nothing can be less than this one. That's all it means. OK. All right. So that was probabilistic data structure number 1. Let's take a look at another somewhat differently. It's also probabilistic, but not in the same way. Like, we're not going to be flipping coins to do it, but they end up calling it a probabilistic data structure. This is another fun data structure that in some sense will blow your mind away because it's different than all the other ones we've done. Okay? This one is called a Bloom filter. Okay? And what it is, it's a space-efficient way of saying, is some member in a set? Okay, I've got a set of things, and this is going to be super efficient and super, like, way more efficient than some other way. So what's a really fast way that we have to determine whether something's in a set? What data structure might we use? Hash table, right? Because it's order 1, and you can say, is it there or not? And it's a constant behavior, right? The problem with a hash table is that it takes up a lot of space. Every element that's in the table is distinctly represented in the table, right? There's not much way you can get away around that, right? I mean, you can have the hash values be such that it's just the hash values. That's not too bad. But in some sense, you've got to say that every value in the array could have an object in it, and you have to keep that whole array, and whether those and that's a fair amount of space, right? With this, what's interesting about a Bloom filter is it's not perfect. Like, you can't say definitely for certain that an object is in the set. Okay? You can definitely say that an object is not in the set, but you can't say that an object is definitely in the set. Which is interesting when you think about it. I mean, sometimes you might have to think about, what are some use cases of that? When might I care that something's maybe in the set but definitely not? There are. And I'll give some at the end. Give some examples at the end, OK? But this is the probabilistic part of it. You have to say, well, it's probably in the set, right? But you're not sure. OK? So this is how it works. It's really cool. OK? We call those false positives. In other words, if I say, hey, is object X in the set? And you say, probably, that's a false positive. In other words, you say it is, and then it might turn out not to be. OK? Those are possible. So if you don't care that something is in the set definitely, but you care that it's not in the set definitely, those would be called false negatives, and you can't have those. So if I tell you what you're looking for is not in the set, you can believe me 100% of the time with these. OK? Everybody get that? False positives versus false negatives? Yeah. No, it's if it's not in the set. Right, but we're right. So I tell you, so we've got a set of numbers, right? And you say, hey, is 7 in the set? And I say, no, it's not. You know it's not. You can take that to the bank. You can say, it doesn't matter.
If you don't say no.
If I say it might be, or I say it probably is, then you can say, OK, 7's probably in the set. It might not be, but you could say, but I've told you that it's likely to be. So there's the probabilistic part of it.
So in this case, yes, it's in the set means yes, it's probably.
Yeah, yes, it's in the set means yes, it's probably in the set.
Right.
Yeah, exactly. Charlie?
You just asked the question,
No, because you can only ask whether it's in the set. It doesn't say, you can't ask whether it's, was that your kind of your question? Yeah. You can't say, is this one not in the set, and it says yes. Like, that doesn't make sense. You got to say, is it in the set, and it either says yes or no. And if it's yes, you can't necessarily believe it. But with high probability, you can say, yeah, it's probably not, depending on the parameters, which we'll get to. Alex, you had a question? Okay.
Sorry, it was the
Same question? Yeah.
But if it's, what else can it be besides in the set or not in the set?
It can probably be in the set. We'll see. I'll show you. You'll see. Okay, you'll see. All right. Well, the nice thing about allowing for this, hey, it might be in the set, and it probably is that you can compress these extremely well. Okay, you can actually get up to 32 times compression on these things, right? Which is huge, right? What we do is we have this thing called a bit array, which I'll show you in a second. Okay, and you definitely need more than 1 bit per element, but you can shrink these things like a ton. Okay, let me show you what this means. You start out with a bit array. What this all this is these are individual numbers. They're either ones or zeros. That's it. Later we'll talk about a counting Bloom filter where they can be more than just ones or zeros. But for now, ones or zeros, and that's it. Okay, that's a bit array. So if you ever decide to set one of these, you're going to set it to 1 or you're going to set it to 0. That's it. Okay. What we do is we say, okay, start with an empty array. So start with an array of all zeros. Okay. We still have hash functions. We have some number of hash functions. Okay, we're going to call them k hash functions. Okay, in this case, I'm just picking 2 to make this example easy. The first hash function is the one we saw from both of these are from the lab, right? The first one is 13 minus the number mod 13 and then mod 7 because that's the length of my table, right? Should it have been 8? I think it should have been 8. Yeah, it should have been 8. Sorry, forget it. 7 will probably always stay 0 because of the way I've done this. And then the second one was 3 plus 7 times the number mod 7. Okay, so pretend this is a 7 instead of an 8 element array. What you do is you have some number and you apply both hash functions to it. And if those hash functions are supposed to go in a certain bucket, what do you think you do to that bucket? Turn it to a 1. Okay? So what you do, well, the hash functions, by the way, should be independent, meaning that they should be as, like, you hope that they won't necessarily hash to the same bucket, but if they do, that's okay. But they probably should be very random, right? You can actually calculate the length of your table versus how many hash functions you should have. But there is a optimal amount. But I'll let you go look at Wikipedia for that. Okay, so you hash them. And what you do is you set them to 1 if both hash functions go in those buckets. And then, well, let me show you the example first. We take a number. We want to hash 129, or we want to put this in the Bloom filter. For the first one, 129 with this first hash function, right, gives me 1. So I set this bit equal to 1, right, because it's 1 here. And then the second hash function is 3, so I set this one equal to 1. Now this is what our Bloom filter looks like. If I were to now say, is 129 in the Bloom filter? How do you think I'd figure out if it's there? Yeah. Yeah, you rehash them. You rehash it, and then look and see if both are 1. And if both are 1, we're going to say it's in there. We're going to say that that's what we're going to report. Right? Whether or not you believe me or not is a different story. But we're going to say that it's in there. Okay? Let me show you another example. Or the next one. I know, this is one where you go, oh, I get it. Right? So for 483, right, I hashed it to, the first hash function gives me 4. Second hash function gives me 3. Okay? And now how many bits are done? This one, and this one. Okay? Yeah.
What if we add 2 things to the hash that both have 2 things to the table, both have the same hash value? The first one sets to 1, the second one just keeps it at 1. And then we say, is this set, and then we say like.
Let me ask this. I see where you're getting at. Let me ask this in a slightly different way. Let me ask your question. Let me see if I can ask your question in a slightly different way. What if I have another number, say it was 822, that set this bit and this bit? What would I report if I was looking for it? If I was looking for 822, I would say yes. Did we put 822 in here?
Oh, you're setting multiple.
We did not. We're setting multiple bits. Okay, we're always setting the ones that these two hash functions determine that we're going to want. Yeah?
So is there an optimal amount of uses for the bloom filter? Because right now it's 1, 0, 1, 0, 1, 1, and there's a bunch of zeros, but it seems like the more samples you have, the more likely the
More likely a collision is. Yeah, you can. We will figure out the probability of a collision of a false positive in a minute. Okay? Yeah.
Can we model a really compressed bloom filter using a Boolean filter since it's
Yeah, absolutely.
true or false?
You can model this as being one number that's all the bits.
Is that better than using would that be better for using ints if we were using C++? Would it take up less space?
It would take up less space. It wouldn't necessarily take up less time, but it would take up less space. Yeah. Yeah, sure. Okay, so we've added two things so far. We've added 129 and we've added 483, and these 3 bits are set. Okay? Is 129 in there? 129, we set bit 1 and bit 3, and this is exactly what Alex was asking. And look, 1 and 3 we report, yeah, it's probably in there, even though it's not. We report that it is. So that's a false positive. Okay? Probably in the table. Or did we put 129 in there? We did put 129. Sorry, we did put 129 in there. So it's probably in the table because we check it. 123 is 123 in the table. 123, the first hash function goes to 0. The second hash function goes to 3. Is this one in the table? Absolutely not. How do you know it's not?
Because one of them is not.
Yeah, because this one's never been set to 0. Had it been in the table, it would have been set to 1. So therefore, 123 cannot be in this table, and that's not, so there's no false negatives on there. Yeah?
But what if there was another value that we didn't add that would have set 1 and 3 to 1?
So what?
And then we asked if it was there.
Yeah, that would be a false positive. We would say yes, and that's a false positive. False positives are allowed. False negatives don't occur because you can never.
Every time we add it, it flips the values.
Yeah, every time you add it, you always flip to 1. You never flip back to 0. In fact, that would be important to recognize. Yeah.
So basically it doesn't handle collisions.
You can think of it that way. You can say, oh, look, it doesn't handle collisions. But it does more than that, right? We have a really shrunken table here, and it gives us pretty good. It's not like we're just doing one hash function, which you could. You could build a Bloom filter without collisions and call it and only have one hash function. And it would be very rare that you'd have a false positive, but the problem with that is it's going to be big. This compresses it a lot. Because in order to store each value would get its own bucket basically, except for collisions. So it's going to be bigger. It's not going to, and these are only 1 bit too. It's not, you don't have to store the actual value. I guess you could do the same thing in a 1-bit Bloom filter with 1 hash function is a Bloom filter. It's just not as efficient because the false positives would happen probably more often actually.
Oh, it's because
Yeah.
now we check for both.
You're checking both of them, and it makes sense. Yeah.
So would you always have to use a Bloom filter in conjunction with some other data structure? Because all this is telling you is like.
Yeah. Well, it depends. That's a good question. Let me give you an example of when this is used. If you do care that whether it's absolutely there or not, you would need some other function or some other data structure. But here's an example. So anybody use Google Chrome? Right? Use Google Chrome. So Google's nice enough that when you go to a website, Google wants to tell you whether that's a malicious website. Okay? They say to you, maybe you've gone to one before, it puts up a screen that says, stop. We suggest you should not go to this website because it's bad news. It's got malware on it, or it's got something that's deemed bad by Google. Right? Now, you could, on your own local computer, keep an entire hash table of all the 10 million websites that are considered malicious, right? And you'd store that on the computer, and you'd check that each time, and you could use a hash table, but it'd be a pretty big table, right? A million, you don't want another megabyte worth of data. In a very small Bloom filter on your computer, Google can say with high probability whether or not the site you're going to is malicious. It will always report not malicious if it's not malicious. If Google thinks it's malicious, it will report probably malicious, right? If it reports probably malicious, Then Google goes to their webs, like they go to their servers, look at the real list, which has all of them, and does a double check. And then if it comes back as malicious, it will say this one's malicious. So that is a backend, but it makes it so you can have a tiny little Bloom filter on your computer that's hashed a million things, and you can have a high probability of getting it right. And so it saves a lot of time. Okay? Google has lots of uses for these. Whoever like works at Google on these things loves Bloom filters because they use them a lot for various like database queries, right? Database queries, they'll say, look, does this exist? Yeah, probably, and then you deal with it, and if you need to, go to a different list or whatever. Okay? So does everybody get how this one works now? It's pretty cool, right? Let's see. 100, 1 and 3. We have not put 100 in here. 1 and 3, guess what? It was a different set of bits than any of the other ones we set, I think. I don't know if any of the others came out exactly, well, maybe they did. 1 and 3. But 100 says, hey, it's probably in the table, but it's not, as it turns out. That's a false positive. Okay? I'm not connected to the internet. What's going on here? Probably because Google thinks it's a malicious site. There's an online Bloom filter checker. In fact, I don't think we need to necessarily do it right now. I'll show it to you if I can get connected here. But there we go. Let's see. Hang on. Okay. This actually demonstrates it for you. And what you can do is you can plug in some strings. Somebody give me a string. Apple. Right? You add Apple to the Bloom filter and see it changed a couple of blocks in the Bloom filter. Those 2 bits got changed. Right? Somebody give me another one. Dog. Let's see. Dog sets these bits here. The green, these 2 here. Right? So now we've got 0, 1, 2, and then 11 out of a total of 15. Right? And it keeps doing that. And what's cool is once you do that, let's add a couple more. Tufts. Right? Add to the Bloom filter. Oh, a couple that overlaps there. And then Jumbo. Right? Add that to the Bloom filter. Okay, so there's the Bloom filter now, right? And it actually, when you go down, it tells you what the probability of a false positive is. Because mathematically, we can figure out what that probability is. I've added, how many things did I add to that? 5? I've added, 4 things to that list of only 15 elements. And I can get a false positive rate of only 16%, which is pretty good, right? So if I check, and remember, if it's not in the set, it will report it's not in the set, right? So cat is not in the set, right? It tells me that, immediately. And we know that's true, right? And then let's look at dog, because we already put that in there, right? Dog, maybe it's in the set, right? Just says maybe. That's it. It should make it different enough, yeah. It's not in the set. Yeah, it does generally makes it different enough. Okay? All right, so go ahead and play around with that if you want. And you can see how that works. Now, a few minutes of mathy bits. Okay, let's figure out what this probability of a false positive is. Okay? All right, bear with me on this. You ready? If you have m bits in the array, without knowing anything about how they got there, okay, just saying random, we'll say that it's random, the probability that a bit is not set to 1, in other words, it's 0, is 1 minus 1 over the number of bits. Okay, because each bit has 1 over m probability being set. 1 minus that is the probability that a particular bit is not set. So far, so good? Okay. If we have k hash functions, each hash function, as long as they're independent, should, on average, put them in different bits. So we need to raise that 1 minus 1 over m to the kth power, because now we're going to say, well, the probability that a bit is not set to 1 by any of the hash functions is slightly bigger. Okay, to the number of hash functions we've got there. Okay, so now we take a look at if we have put n items into the hash table. You don't have to write all these down if you don't want to. It's on Wikipedia or on the slides here. If you've inserted n elements, well, now you've expanded the probability by another factor of n, right? Because each one was 1 minus 1 over m to the k, and then you've done n of them, so you got to raise that whole thing to the n. Okay, and we're still deciding whether a bit is 0 or not. Given this, what would the probability of a bit being set to 1 be?
1 minus
1 minus this whole thing, right? So now you've got the probability that you've got a 1. Now remember, we're trying to figure out the probability of a false positive. In other words, the number of 1s lined up perfectly, right? So that we had a false positive. So we ended up saying it's probably in the table when it wasn't. Okay, probability of bits 1 is 1 minus that function there, right? And then you have to test the membership of an element that's not in the set. So what you do, right, for each of the positions you've done a hash on, right, you had that probability. So now you're going to do, so that's another bunch of hash functions. You raise that to the k value, right? You raise that to the number of hashes that you've done, and you get this probability here. Okay? You can actually approximate it with a little exponential function here, if you want. Okay? Not sure why I'd necessarily do that, because this is pretty defined. But this is all assuming that your hash functions are independent, and you've put n elements in the table. The table is m amount wide, and you have k hash functions. Okay? So this is the result. That's how they calculated the probability of a false positive on that web page. Okay? For the previous example, this is actually wrong because I only had m equal to 7 because I screwed up my modulus there. But if we had m equals to 8 and I did it right, the false positive rate is 17%. Okay? If we added 2 items. Okay? Just do the math. And it comes out like that. Right? So it's not so bad. Math is easy. I mean, this is a one-liner in a program if you want to figure out the probability of being false. Yeah?
So
False positive.
Since these can be compressed so much,
Mm-hmm.
what we should be doing is just having tons and tons of bits so that we never...
Right.
It goes down to near 0.
Right. The more bits you have, the more likely you're had.
No, it's smaller.
Well, it gets smaller, but you also should increase the number of hash functions you have too.
Right.
Okay.
You'll be flipping more.
Yeah, you're flipping more bits and making it so that your odds that it's you're going to compress it more. In other words, so in this case, so now you've got 17%. Yeah. So if you have a lot of bits, you'll be all right. Now this can store a ton of stuff before this gets big. I mean, if you have if you have a bit array that's 10,000 long or something, you can store a ton of things before you care much about this false positive rate. Okay, it's pretty neat that way, and you can do some of the math on that if you want. There is another downside besides these false positives, right? I've given you the example here, right? The negative is you can't remove anything from a Bloom filter, right? You're not allowed to, because the minute you try to remove something, you could remove something else, right? And you're not allowed to have false negatives, right? So if you remove something and then something else also gets removed, and then all of a sudden you're reporting that it's been not in the set, that's a false negative, and you shouldn't have that. So you can't do that. You can't remove from a Bloom filter. Okay? You could keep a second Bloom filter that has all the false positives, but then false positives there become false negatives, or false negatives there become false positives. I guess it's false positives become false negatives. It gets a little hairy in that way. Yeah?
If you really cared, like, you could just remake your Bloom filter that you're just using hash functions.
Only if you kept a list of all the ones that actually are in it. So you got to keep a list. Yeah. Now
If
there.
you're Google and you have that list on your server.
Yeah, you could redo it. Yeah, you could redo it. Yeah. So that's one way to do it. There is a thing called a counting Bloom filter, which basically means instead of having ones and zeros, instead of doing bits, just make these actual integers for every one that you add, and then every one you take away, like if you want to delete, remove something, you'll decrement this, and the only time it ever gets back down for both of these to be 0 is if there's nothing left in those bits, and therefore it would be okay to have it removed. Yeah.
Well, I guess, but what if you were trying to remove something that never added?
You wouldn't be able to remove something that's never added. Yeah, that's a good point. You're not allowed to do that either. Yeah. Yeah. Last question.
What's the compressibility if you have calculators?
These would all have to be integers, so it's not like 4 times instead of whatever, instead of 32 times or something like that. Yeah. Okay. Any other questions? All right, guys. See you tonight if you want to come to the session on hash tables, or have a good Thanksgiving otherwise.